which are most expected and previous year questions. Now let's start. Question one is a five-stage pipeline processor has instruction fetch and instruction decode stage, operand fetch stage, perform operation stage, and write operand stage. All the stages take one clock cycle each for any instruction except the PO stage take 3 cycles. Basically every stage takes 1 cycle and PO stage takes 3 clock cycle in add and subtract operation and 2 and 1 clock cycle in multiply and divide instruction. So these are the instruction I1, I2 and I3, I4. So first I1 is when executed it will take 6 clock cycle, mm, mm, 2 clock cycle of PO stage, so it takes 6, and I2 is not dependent on I1, so it takes 5 clock cycle, and I3 it takes three, 2 extra cycle which are stalls. It create 2 stalls, and I1 also create 1 stall because it takes 2 cycle time of PO stage, so I2 did not get PO stage after release. When release I1, then I2 get from after execution of I1. So then one stall is created here, and I3 here, also 2 stall created because it takes 3 clock cycle, and I4 it also takes 3 clock cycle, it also create 2 clock cycle. Total 5 stalls is created in this instruction, and if not stalls, then if not stalls occur, then clock cycle will be counted, occurs, 8 clock cycle will be takes to complete this instruction if stalls are not occurred. But there is a stall 5 cycle stall, so it will also concluded, so it will total takes 8 plus 5 13 clock cycles. In this way I solve this question. Now next one is consider 16-bit hypothetical CPU which support one word instruction. Instruction contain 8 bits. It questions ask basically 16-bit, it contain words instruction, 16-bit instruction in which 8 bits of code and address field instruction is stored in the memory with starting address 800 decimal. So I solve in this way. First instruction is 16-bit, it will divide in 8 bits, 8 bits and 8 bits. So in memory at 800 I1 instruction and 801 I1 of address field and 802 next instruction. So when instruction fetched, program counter will from here to here because it exchange the data of block size. Block size is 16 bits. So target is equal to PC plus relative value. If we calculate, PC is 802 after executing this instruction. 802 plus relative, I don't relative to calculated. Target is given. Target instruction control will be transferred to 512 locations. So this is the target location. So I will put here, then I will get relative address minus 290. So minus 290 is correct answer for this question. Now next one is a 500 megahertz processor was used to execute the program with the following instruction and their clock cycle. And these are the instruction type and instruction count and CPI. CPI means one instruction takes one cycle, two cycle, and basically it asks for MIPS, millions of instruction per second rate for this program. So for calculation of MIPS, we first calculate cycle time of one instruction 2 nanosecond, then calculate average CPI. Average CPI means types of instruction multiplied by cycle in one instruction. So divide it calculate the sum of overall cycle, total cycle divided by number of instruction. I will get average CPI. Now average CPI 1.62 cycle. Average instruction execution time 1.62 cross to 3.24 nanosecond. First instruction takes 3.24 into 10 raised to power minus 9 second. For number of instruction in 1 second, 1 by 3.24 cross 10 raised to power 9 instruction per second. For converting in millions instruction per second. For converting in millions of instruction per second, I will first convert in 1 second number of instruction and then convert in million of instruction per second. I will get 308. Now next one is a hard disk has 63 sector per track, 20 platter and each with 2 recording surface and 1600 cylinder. It basically asks for the sector number corresponding to the this address. So for this I will calculate it in this way. For 600 cylinder means in 600 cylinder it this amount of sectors, and in 38 surfaces means 30 in 38 surfaces contains 2394 sectors and 47 extra sectors. So total sector will be 151441. This is the sector of this address. Now next one is consider a computer system with a byte addressable main memory of size 232 byte and 64K byte data cache memory with block of size 64 byte. Tag field length is 18 bits. Which are the following? For this question I will solve this way. 32 bits virtual address to port 32 memory size, 32 bits virtual address, block size 6 bit, number of index. For number of index bit, this is 16 bit. It takes 16 bit for storing and minus block size. I will get index bit 10 bit. Now 32 is equal to 18 plus 6 plus x. Yeah, it will give set bit. Set bit means this is 18 is basically tag bits. 18 is tag bits and this is block size bit plus x. It gives set bit. Set bit means set number bits, and this is the index bit. It cache bit, cache line bit. So after subtracting 10 minus 8, we get 2 bit for associativity. So it means four-way set associativity. In this way, I solve this question. Now next one is consider 32 bit register which store floating point number in single precision with the value of 32 bit, 0 sign bit, exponent bit, mantissa bit. For this question, I will solve by this way: -1 for converting 32 IEEE single precision format by this way: -1 sign bit, mm, again bracket 1 point mantissa into 2 exponent minus 127. Exponent is here, mantissa is here. When we put the value, I will get 58. In this way, I solve this question. Now, next one is consider 24-bit hypothetical CPU with support 1 word long instruction and 16 KB memory space. If there exist 99 one address instruction, then how many zero address instruction are formulated? For this, I will solve by this way: 99 one address instruction into multiplied to power of 14 for addressing plus x is a zero address instruction. So by calculating this, I will get 25 into 2 raised to power 14. So option C is correct for this question. Now next one is choose the correct statement from the following regarding RISC and CISC architectures. So CISC contains smaller instruction set. No. RISC contains larger instruction set. No. Expand opcode technique is not needed in CISC architecture. Yes, this is true. Expand opcode technique is not needed in RISC architecture. No, needed. This is false. Only option C is correct for this question. Now, next one is consider the following program segment here: R1 and R2 are general purpose register of memory. Location 3 and 3000 is 25 and location 2 and 2000 is 17. Content of register R2. All the number are in decimal. So after performing these operations, after execution of program, what will the value in R2 is? The value in R2 register. What is the value in R2? Initially R1 R1 is equal to 9. Then after 9 decrement R1 9 and then decrement and then condition check. After condition on R1 for non-zero, this condition check, jump on non-zero y, jump to y here. If non-zero, so this is non-zero, so jump it, loop continue 8 times, so 8 times minus in R2 contains 120, 120 minus 8 cross 17 is equal to minus 16. I will get. Then next iteration is R2 plus M3000. There is 0, so it will not jump. Then R2 will add in M3000 location content, so it will get in R2. In R2 it is 9. Then jump on Z, and this is stop, and then stop. So R2 is equal to 9. This is the answer of this question. Now next one is consider a microprogram control unit which supports 64 distinct instructions. Among all instructions, 16 instructions need a sequence of 16 micro operation to execute. 24 instructions need a sequence of 20 micro instructions. Basically, it is asked for how total control memory required for such system. So first I will find the number of micro operation, total number of micro operation to be stored, 16 instruction and 16 micro operation. 16 instruction needed a sequence of 16 micro operation, then total number of micro operation. 16 cross 16, and then 24 instruction needed 20 micro operation, 24 into 20, and then to execute, and the remaining 12 micro, 24 into 12, total I get 1024. Now for this, uh, total number of words in control memory, 2 raised to power 10, 1024. In this way I solve this question. Now next one is, consider a hard disk. Basically hard disk is given, and the file size is given, and last address after putting the file in disk, this is the last address. It will ask for first address of file. So first sector address of file is calculated by this way. First we last sector for the file. This is the last sector. By using this address to calculate last sector, and then size of file is this, sector number of first. So on minus from file size plus 1, I will get sector number of first sector of the file. Then it will convert into cylinder number and surface number and the sector number by divide and modulus. I will get this address. This is the first address of the sector. So in this way I solve this question. Now next one is, there is a computer system which has 22 bits instruction and 9-bit address. It supports 2 address instruction and 1 address. Both there are x number of 2 address instruction and maximum number of 1 address instruction can be formulated. For the question, Tripti has given an answer A1 and Rupam has given the possible maximum difference. It will ask for maximum difference. So for this question I will solve by this way. 2 address instruction let x and 1 address instruction let y, and then solve this equation. I will found for maximum y, put x is equal to 1, y is equal to, I will get 7680. For minimum y, put x is equal to 15, I will get y is equal to 512. So maximum difference is 7168. In this way I solve this question. Now next one is, consider a device operating on 8 Mbps rate and transferring the data to memory using cycle stealing mode. If it takes 0.5 microsecond to transfer 16 bytes data to memory when it is ready for prepare, then the percentage of time CPU is blocked due to DMA. For this question I will solve by this way. For 16 byte data transferring or prepared time, first I calculate prepared time. 16 by 8, I will get 2 microsecond, because 16 by data 8 megabytes, I will get 2 microsecond. Percentage of CPU block transmission time by my propagation time into 100, I will get 25% CPU block. Yeah. By this way, in this way I solve this question. Now next one is, consider a magnetic disc with X platers, each with 2 recording surface. Each sector has equal capacity of 1 kilobytes. If total capacity of the disk is 240 gigabytes, total number of surface on the disk is total capacity 240 gigabytes is equal to surface, total surface on the we know that total capacity will calculate it into surface into multiply track into sector into one sector capacity. We will get total capacity. Then 240 GB is total capacity. Then this is equal to this. Then for total surface, I will divide by this. I will get 30. In this way, I solve this question. Now next one is, Now next one is a computer had 256 kilobyte four-way SATA associative write back data cache with block size 32. The processor sent 32-bit address to the tag directory entry contains in addition to address tag to a valid bit, one modified bit, one replacement bit. So for this question I will solve by this way. Block size 32 byte. I will get 5 bit for block size. Index bit I will get 13 bits. This is the cache size and this is block size. Four-way set associated. Then I will divide the 13 bit by 2. I will get 11 bit for set set number. So tag will be 32 minus 11 minus 5 16 bit. So in this way I solve this question. Now next one is in design a computer cache system, the cache block or cache line size is an important parameter. Which of the following statement is correct in this context? Then smaller block size incurs lower cache miss penalty. Yes, this is true. Smaller block size implies better spatial locality. False. Smaller block size implies smaller cache tag. False. Smaller imply lower cache hit time. False. Only option A is correct for this question. Now next one is in a k-way set associative cache, the cache is divided into V set, each of which consists of k lines. The lines of a set are placed in sequence one after another. The lines in set S are sequenced before the line in set S plus 1. The main memory blocks are numbered 0 onward. The main memory block number Z must be mapped to any one of the cache line. It is basically asked for to the range of this set size. For set number, we know for set number we Z is a Z is a block number. J is a block number. J mod B. B is a set size. Set size number of set into K. K is K is set line. 2 J mod V into minus 1. It is the range. It gives the range of set because in up to K up to 0 to K minus 1 the range of the set 0 to K minus 1 it will range of the set to store the value. Now next one is for this question option A is correct and remaining are not correct. It will not give for the now next question is a RAM chip has a capacity of 1024 watts of the 8 bits each 1K cross 8. The number of 2 cross 4 decoder with enable line needed to construct a 16K cross 16 RAM from 1K cross 8 RAM. For this question I will solve by this way. Number of chips. First we calculate number of chips. 16K divided by 1K cross 8. I will get 32 chips which are in 16 rows and 2 columns. To create in 16 rows and 2 columns it uses 10 address lines for 1K. It uses 1K in chip, so it uses 10 address it uses 10 address lines. So for 16K words it takes 2 power of 14. So for 4 to 16 decoder is used. 4, 4 to 16 decoder is used. So we use 4 to 16. Then 16 divided by 4. I will get 4. 2 to 4 decoder and one decoder at first level also used for adding these four decoder. So total 5 decoder I will use for addressing these chips. Now next one is an 8 KB direct map write-back cache is organized as multiple blocks, each of size 32 bytes. The processor generates 32-bit address. The cache controller has one valid, one modified bit as many identify memory block. What is the total size of memory needed at the cache controller? So for this question I will solve by this way. First we calculate the number of cache block, then block offset, then number of index bit 8, and then after I will calculate tag bit by total minus index and block offset. I will get 19, and then add the one valid bit and one modified bit, then I will get tag bit in one for one entry, tag size for one entry. So total size for total entry 256 cross 21, then I will get 5376 bit. Now next one is 20. A main memory unit with capacity 4 MB is built using 1 MB cross 1 bit DRAM chips, 1K rows of cell with 1K cell in each row. Time taken to single refresh operation 100 nanosecond. So total 1000 row. So for total refreshment, I will solve by this way. DRAM chips 1K cross 1K cell. The number of rows in one chip 2 raised to power 10. Total time taken 100 cross 2 raised to power 10. Then these are in nanosecond. 2 raised to power 100 cross 2 raised to power 10 nanosecond. So this is the option C is correct for this. So option B is correct for this question. Now next one is a computer system has an L1 cache, L2 cache and main memory unit connected as the block size in L1 cache is 4 words, the block size in L2 cache is 16 words, the main memory access times are 2 nanosecond and 20 nanosecond and 200 nanosecond for L1, L2 and main memory, which they are missed in L1 cache and 8 in L2 cache. A block transfer from L2 cache to L1 cache. What is time taken from it? Will ask for when mm, miss in L1 cache and then hit in L2 cache, then time taken to transfer the block from L2 cache to L1. So first I will tell you L1 has forward block size but L2 has 16 word block size. Then L2 always send L1 block 4 words, which is equal to L1 block size, not its own block size. So it will take 20 nanosecond when L2 has hit, so it will take 20 nanosecond. It is so simple, it is only lengthy. So option B is correct for this question. Now next one is match the following. Implied mode is related to register which are CPU register specific in a specified implicitly in the definition of the A related to 4 and then immediate specified in the register. B register which are in CPU. C first and the register indirect. Register specify the D second. So option A is correct for this question. Option A is correct for this question. Now next one is in the big Indian system the computer store MSB of the data in the lowest memory address of the data unit. True. MSB are stored in lowest memory address. So for this question is only option A is correct, not LSB of the lowest memory address. This is false, this is false, this is false. So that's all about COA. These are the most expected question. For later update, please follow, comment, subscribe my channel. Thank you.